In the last lesson, we looked at an example associated with aluminum cyclic test data where X was our number of cycles to failure. We're going to turn in this lesson to what do we do with those descriptive statistics that we determined last time, such as we defined the sample mean as being the sum of all of the individual observations, and then we averaged those 1 over n. We had 70 of those. In that particular case, it turned out to be 1403.6 cycles to failure. We also defined the sample variance as being the sum of the square of those xi's minus n times the sample mean squared all over n minus 1. Right? That actually looked a little bit different because that's the same thing as the sum of xi minus the sample mean squared, and we divide that by n minus 1. Those were the same equations as we worked them all out. Right? And out of this arises a number of questions for which we are going to be interested in the answers, of course, and such as how representative is this n equal to 70 set of data to the or of the actual population. We developed a whole bunch of descriptive statistics, not only here of sample means and sample variance, but also the histograms, the cumulative functions. We might have looked at probability paper, all of it to give us some sort of hint about what that data looked like, but is it representative of the actual population? Other more detailed questions might be how close is our observed mean or sample mean to the true mean? Or how close is our sample variance to the true variance? Or ancillary kinds of questions are sample mean and sample variance the best estimators of the true mean and the true variance? It seems natural to use those, but are they the best? Are there others out there that might be more effective? And when you get into other ways that we might look at the data, then we might have different ones, different statistics. That's what x bar and s squared are, the sample statistics. There are other parameters that we might be looking at. Maybe it's kurtosis, maybe it's skewness, maybe it's other manipulations of the x's, maybe putting a square up here, a cube up here, to the 4th power, maybe it's the square root of that number. Well, what might we be looking at is going to be driven by the underlying distribution model that we might be interested in. Right? And then the bigger question then is, how do we infer from this data set, so that's the x1s up to the xn's, what the true population distribution and its associated parameters are. Right, and that is really what statistical inference is. Little slip of the tongue, I said interference, because sometimes this stuff does seem to interfere with your life and your mind. Right? Statistical inference is inferring from the statistics, these sample measures, the sample data, what the true population might be. And these larger questions, all of these kinds of things, that's really what the central focus of the rest of the course will be, is all about that. We'll still have a little probability to work with, but there is a subtle and yet important difference as we shift away from probability and start looking at actual data and get significantly involved with that. So there's a little bit of formalism we want to make out of this before we charge into some of the approaches. That we're going to pursue, and it's going to carry us through about 5 to 6 different chapters ultimately. Not here, of course, in this module, but in this module we'll be just focused on the chapter 7 before we head off into hypothesis testing. Okay, so let's look at what exactly is a random sample. And so our sample data, x1, all the way up through xn, are a random sample if they come from the same population, right, and selected, the right word to say is randomly, but what we mean by that is that they're statistically independent from each other. So if there's an order or a sequence to how they're pulled out of the population, then they're not really a true random sample, they're something else. And that would alter, if there is some sort of systematic way there, that'll alter what we get out of the numbers. For instance, the classic example is that when the draft was used in the 1960s, that the way that the draft numbers were selected was initially, it turned out not a random selection, and so you found a disproportionate part of the population was being pulled into the military. And of course, because of the conflicts at that time, and an unpopular conflict, that was relatively big news, and all kinds of theories of conspiracy and that sort of thing out of what was really a mathematical error were charged, and of course there was a nasty mess that then was changed into a different, more random selection, an independent selection of the numbers. Okay, so x1 to xn are random samples. They come from the same population. They're selected independently. They have independence between their selection. And when we say that they come from the same population, what we're really saying is that they come from the same probability distribution with some set of parameters. Right? So I've written this as capital F. That might be the CDF. It could actually be lowercase f and the PDF if we wanted to. But that's just our notation here for the probability distribution with parameters theta, meaning theta could be more than 1 here. So for example, the normal distribution with parameters mu and sigma, or the Weibull with 2 parameters, delta and beta. So notice we aren't always working with mean standard deviation or mean and variance. Could be single parameter models such as the Poisson with parameter lambda, or back to a two-parameter model, the gamma distribution with parameters r and lambda. Okay, and so here's also one of the differences between statistics and probability. In probability, we assume that we know these things and then we go do a bunch of work. But one of the real challenges in ever using probability models is that we've got to figure out what the parameters are. And then we also have to make set thresholds for understanding how to make conclusions and decisions. Two real challenging aspects about using probability. Well, statistics is all about doing some random sampling and then using that random sample to try to estimate what these two parameters are. Right? And so that's the big thing here in our formalism is then, well, what are these approaches to finding our parameters that we're calling just generically theta. And so the first two that we're going to end up getting into some depth in are the method of moments. We've actually already used this technique a couple of times. The maximum likelihood method. Right, both of these are what we're going to label as point estimates. And they refer to the notion that we use the data for coming up with, for developing a single quantity to estimate the parameter, single value. So when we set the sample mean equal to the true mean, or really the other way around, the true mean equal to the sample mean, then that's a point estimate. And we have just that single quantity. That might seem like, well, what's the big deal here? Well, because there are other approaches that we might use, those being interval estimates. And some sort of confidence that's associated with that. And so now we'll say, well, the true mean might be within this interval based upon this sample statistic. And here's our confidence level that we'll express as like 90% confidence level or 95% confidence, that sort of thing, which is sometimes a misleading type of thing where you say, well, I'm 95% confident that the true mean is in this interval. It doesn't mean that the true mean is 95% probability in that interval. It actually means that was the technique that was used. And we'll get into quite a bit of depth with that later on. Right, now the big thing here is that, okay, well, we have these different approaches, and particularly for these point estimates, there's going to be a concern of, well, do we have a biased estimator, or what is the bias with using a particular statistic, and also questions about error that's related in there. And there's also a little bit of interest to, well, what if I have prior knowledge? How might I use that along with the new data that's been collected to improve my estimate? How does that get combined? That's going to lead us into Bayesian approaches or Bayesian estimators. And then there's also the question of, well, what's the probability distribution of the statistic itself? For example, up above we had said, well, here's the sample mean, and maybe that population was a normal distribution, or maybe it wasn't, but what's the probability distribution associated with calculating a sample mean? Or what's the probability distribution of calculating a sample variance? And oh, by the way, although sample standard deviation and sample variance are related, they're not the same thing. There's a mathematical operation that goes from one to the other, and it's a nonlinear operation. So whatever the distribution is on sample variance, that's not necessarily the same distribution that you have on the standard deviation, right? And that goes back to that whole notion of the expected value of a function is not equal to the function evaluated at the expected value of the individual quantities, right? Goofy little probabababble speak that still is important when we get out into here. So in chapter 7, what we're really going to be addressing primarily is method of moments and the maximum likelihood method. Along the way, we're going to define things such as bias in the error and a little bit of this prior knowledge issue, and also end up talking a little bit about the probability distribution of the statistic. It's not till the next module where we'll get into interval estimates and confidence levels.